Hello friends, welcome to Shiksharthi. In this video, we will be discussing the applications of similarity and basic proportionality theorem. So let's start. So if you recollect my earlier video on similarity and basic proportionality theorem, I had talked about few points. Taking that discussion forward, we will see that both these things, when we talk about similarity or we talk about basic proportionality, it is not only going to be used in rectilinear representation, it is going to be used in curvilinear also. Now when I say rectilinear, I am basically talking about triangles and quadrilaterals and polygons. And when I am talking about curvilinear, I am basically referring to circles. Okay, so the first application of similarity in triangles can be experienced in terms of the section formula or whatever. So let's start. Now if I say this is a triangle and inside this there is another triangle such that the information which is given to us is this. Now what is the information given here? There are two triangles. There is one triangle inside the other triangle such that they share a common vertex. So the point that arises here is there a possibility wherein there is a triangle inside another triangle wherein they don't share the common vertex? Maybe. We can make triangles of such sort as well. But in this case, we are talking about a triangle inside another triangle, which is a bigger triangle, such that the line segment BC is parallel to the line segment PQ. Okay, this piece of information is already given to us. So, can I say triangles ABC and the triangle? So, we are talking about triangle ABC and triangle APQ. Are they similar? Yes. Once I am able to establish the double A link, or I am able to establish what? Triple A link. So, now we had talked about various tests of similarity in the first video, is what we are using. Can I use an SAS here? Now SAS can be used only when the sides are given here, and the given piece of information here is there are two line segments which are parallel. Now when it is already given that there are two line segments which are parallel to each other, the only thing that you can do is you can find out some congruence or similarity in terms of the angles, not in terms of the sides. So you cannot use any other test of similarity other than the double A or better known as a triple A test. Okay. Now once you are able to establish both these points, the first point and the second point, we can establish what? We can establish the BPT theorem, or we can establish the sides ratio theorem. Now the sides ratio theorem is nothing but we say that if these two triangles are similar, AB divided by AP will be the same as AC. AC divided by AQ will be the same as BC divided by PQ. And let us imagine that this ratio comes out to be m:n. This I am assuming from my side. Meaning thereby, this entire, let us say, is M, and this entire is N. So there are two ways of understanding this. Once we know that this is a ratio, either I can assume that this entire length is M and N, or I can say the length would be proportional to M and proportional to N. Now the moment I say proportional, that means I need to use a proportional constant if I am looking for the exact value. So you will see here now the application of ratios comes into picture. So ratio, proportion and variation they go hand in hand with 2D and 3D geometry. Okay, the point that I am trying to make here is, which I have already made in my earlier video, is if this ratio comes out to be m:n and we know that these two triangles are similar, then the ratio should not be 1:1. Or if this fraction, you consider this as a fraction which is m divided by n, it should not be equal to 1 for similar triangles. When does it become equal to 1? It becomes equal to 1 only for non-similar triangles. And when you are using a word like non-similar, it means what? Congruent triangles. Okay. Now, if I drop a perpendicular from a common vertex, now here the common vertex is A. If I drop a perpendicular from here, naturally this will act as a perpendicular on BC as well as PQ. Why? Because both the lines are parallel, both the line segments are parallel to each other. So when there are two line segments which are parallel to each other, a common perpendicular, if there is a perpendicular which is dropped on one of them, it becomes a common perpendicular to both. So let us say AD is the perpendicular for the triangle ABC and AE is the perpendicular for triangle APQ. So at the same time, using the same property, which property? I can say if I talk about triangle ABD or if I talk about triangle APE, or I talk about triangle ACD, analogously I talk about triangle AQE. So can I say these two triangles will be similar? I am talking about triangle ABD is similar to triangle APE. At the same time, triangle ACD is similar to triangle AQE. Yes. And thereafter you can establish the side ratio link, which is nothing but basic proportionality theorem, basic proportion, the proportion of the sides. Keeping in mind that since these two triangles are similar, even these two triangles are similar, so the fraction cannot be equal to a 1 for similar triangles. Keeping this thing in mind. Okay. Now, once you get all the three ratios, you're getting a ratio as m upon n, or you're getting a fraction as m divided by n, x divided by y, and a divided by b. So can I say all these three fractions or ratios would be the same? Of course. And let us take them as a common ratio. Let us say that all these three are equal to k1 by k2. Now what am I trying to say? I am trying to say that for two similar triangles, the ratio of their sides will be equal to the ratio of their heights. The ratio of their sides will be equal to the ratio of their heights. So when I say AD upon AE, this becomes the ratio of their heights, and thereafter if you divide a triangle into various parts, and if you are able to prove that this part is equal to, this part is congruent to this part, then the ratio remains as the ratio of their sides only for further similar triangles. Okay, now once you are able to establish this, let us talk about another property. So if I talk about property of ratios, see this property in isolation first, then we'll combine it with this. So if I say that if A divided by B is equal to C divided by D is equal to E divided by F, this will be the same as the sum of their numerators divided by the sum of their denominators. For this you can check out my video on ratio and proportion, wherein we have already established this property. Now when we say this is just like trying to say, if I am taking the ratio of the sides, the ratio of their sides, I can say this will be the same as the ratio of their numerators divided by the ratio of their denominators, right? Now when I am able to say this, now what is, the ratio of the sum of the numerators divided by the ratio of the sum of the denominators will give me the same ratio or the same fraction. So when I say A by P is equal to AB by AP will be equal to AC by AQ will be equal to BC by PQ. At the same time, I can say all the three ratios are equal to AB plus AC plus BC using this divided by AP plus AQ plus PQ, which is nothing but calculating the perimeter of the triangle. So can I say the same ratio, the ratio that we have got, K1 by K2, will be the ratio of their perimeters as well. So when we are talking about perimeters, I am basically talking about the triangle ABC and the perimeter of the triangle APQ. I'll repeat. If triangle ABC is similar to triangle APQ, we can say that the ratio of their sides will be equal to the ratio of their heights. Yes, will be equal to the ratio of their perimeters, will be equal to the ratio of their areas as well. Now when I say ratio of their areas, we need to just take the square root of this. So I'll repeat once again for your convenience. So you can calculate the area of the triangle ABC. Now what is the area of the triangle ABC? You will say that the area of the triangle ABC is nothing but half into base into height. divided by the area of the entire triangle, which is APQ, which is nothing but half into base into height. Now, can we find out what is the value of AD by AE? The value of AD by AE in any case is K1 by K2. So you'll be able to substitute the value here. At the same time, can you substitute the value of BC upon PQ, which also is K1 by K2? So you'll be able to say that the ratio of their areas will be K1 by K2 whole square. So if I take the square root of the ratio of their areas, that becomes equal to the same ratio, which is K1 by K2. So we have established 4 things. Thereafter we can establish many more things also, but just to recollect the 4 things that we have established once again. So can I say for 2 similar triangles like ABC and APQ, the ratio of their sides will be equal to the ratio of their heights? Yes. Will be equal to the ratio of their perimeters? Yes. Will be equal to the ratio of the square root of their areas? Yes. At the same time, further on, we can establish a relationship between their geometric centers also. Now, what do I mean by a geometric center? If I talk about the point of intersection of their medians, right, which is known as the centroid, or the point of intersection of their altitudes, which is known as the orthocenter, or the point of intersection of their incenters, let's say this in radius, which is known as the incenter, or the point of intersection of the side perpendicular bisector. So when I say side perpendicular bisector, it gives rise to a when side perpendicular bisectors, they intersect at a common point, and that common point is known as the circumcenter. So there are 4 geometric centers. One is the centroid, the point of intersection of the medians. Second, we are talking about orthocenter, which is the point of intersection of the 3 altitudes. Third, we are talking about the point of intersection of the angle bisectors, which is nothing but the incenter. Fourth, we are talking about the point of intersection of the perpendicular side bisectors, right, which is known as the circumcenter. So that ratio also can be established here, and they will also give us the same ratio, but I am not discussing that as of now. That you can take it as an assignment and you can prove it for yourself when you take this learning to a next level. Now, the next application which I can think of immediately from here, though I am not going to discuss this too much in detail, we can talk about the intercept theorem. Now, what is intercept theorem? I extend these 2 points, let us say, and I make another line segment here, given that all these 3 are parallel to each other. So it is given that BC is parallel to PQ is parallel to RS. This is already given. And then you can establish, the similarity link, and at the same time you can establish what? The basic proportionality ratio of the sides. So how many these ratios would you get? One is when you compare the first triangle with the second triangle, or you compare the first triangle with the third triangle, or you compare the second triangle with the third triangle. Once you would have done this, you would have come to a conclusion that because of this you are able to get what? You are able to get a figure which is BCQP. Now BCQP, or you are able to get a figure like BCSR. Both these figures are what? Both these figures are trapezium. Why are they trapezium? What is a trapezium? Trapezium is formed out of 2 parallel opposite sides, and the remaining 2 sides may be at the same angle or may not be at the same angle. Now when we say at the same angle, that means we are talking about isosceles trapezium, or we talk about a non-isosceles trapezium. So from there you can find out the formula for the area of the trapezium thus formed. And how do you find this? Can I find out the area of this trapezium? Yes. The area of this trapezium is nothing but the area of the triangle APQ, and then from there you subtract the area of the triangle ABC is what you subtract. Once you would have done this, you get the area of the trapezium. Henceforth, once such a trapezium is formed, maybe from here you can establish something, and that something is you can calculate the length of PQ. So the length of PQ will be nothing but BP times of RS plus, let's say, RP times of BC divided by the ratio, and the ratio is this ratio. So BP plus RP. This reminds me of a formula in mixtures and allegations. I mean, I'm just trying to give you a hint. So I can combine this discussion of geometry with mixtures and allegations as well. The last but not the least, which is a very important one, which is again an application of similarity or BP, basic proportionality theorem. Okay. So the piece of information which is given here is, we are taking a right angle triangle. We will not believe that this is a right angle triangle until it is mentioned like this. A triangle in geometry, something that looks like to be is not what you are supposed to assume it as. It should be mentioned that it is a right angle triangle, then only I can take it as a right angle triangle. Because if it looks like a right angle triangle, I assume it as a right angle triangle, is a misconception. So please let us not get into these kind of misconceptions in geometry. Unless it is specified that this is a right angle triangle, even if it looks like a right angle triangle, we will not consider it to be a right angle triangle. Please keep this thing in mind. Okay, so it is given here that the angle ABC is the same as angle BDC or ADB, which is nothing but 90 degrees. This piece of information is already given. Once this is already given, this is just like we are trying to have a discussion like a triangle inside a triangle, and incidentally here we are having a right angle triangle inside another right angle triangle, and the common vertex that we have for both the triangles that are formed here, the common vertex would be B for both the triangles formed, right? Okay, now from here, once this piece of information was given, can we establish this piece of information, which is just like assuming the angles? Yes. Once we were able to assume these angles and calculate these values, we'll be able to establish that triangle ADB. Now angle A is angle X degrees, angle ADB is 90 degrees, and angle ABD is 90 minus X. So can I say triangle ADB is similar to triangle ABC? Yeah, then you write down the consequent ratio, and once you have written the consequent ratio, then I'm using these two ratios. Now when I use these two ratios, I'm able to infer this. This is a very important conclusion. That means if I have a right angle triangle inside a right angle triangle, I can say this side whole square, which is AB whole square, is nothing but AD, which is, when I'm talking about this triangle, so it will be this length into this entire length. Let's say if this ratio is m:n, I'll be able to say that AB whole square is equal to m into m plus n. Now at the same time, can I establish that triangle ADB is similar to triangle BDC? Yes, based on AA property, which is the AA test. And why are we using AA test? Because the angles, one of the angle was already given, and with the common vertex we could have established that both the triangles are similar. Okay, once you are able to find this out and then the consequent ratio, you can say that BD whole square is equal to AD into DC, right? Which is just like saying what? M into N. From here I get some hint of geometric series. Wherein if there are three terms A, B, C, they have a common ratio, and common ratio means what? B square becomes equal to the product of the extremes. So if there are three terms such that they have a common ratio, let's say the three terms are A, B, C, such that they have a common ratio. The common ratio here means B by A is equal to C by B. So then I'll be able to establish a geometric series which is B square is equal to A into C, which is nothing but this. Okay, last but not the least, because of these two things, this comes as a consequent. Which are the two things that I'm talking about? I'm talking about triangle ADB similar to triangle ABC, and at the same time triangle ADB is similar to triangle BDC. Because of this, now their left hand sides are the same, you can just compare their right hand sides. So if the left hand sides are the same, comparing their right hand sides, I can say triangle ABC is similar to triangle BDC, is what I have done, and then their consequent ratios. So from here you get again an important thing. What is the important part here? BC whole square. Now BC whole square should be equal to n into n plus m. This is very important thing, and The last thing to be considered here is, from here I can establish the Pythagoras theorem. How can I establish a Pythagoras theorem here? I can say that now AB whole square, I can use these values. So I can say that AB whole square plus BC whole square. Now AB whole square is just like saying what? M into M plus N. So from here I'll be able to say what? This is M into N. I'm sorry. So AB whole square. So from here I'll be able to say this is M plus N times of M plus N, which is M plus N whole square. And how much is M plus N whole square? Which is nothing but AC whole square. So a very important conclusion from here also, I can prove that the property of a right angle triangle is the sum of the square of the perpendicular plus the square of the base gives me the hypotenuse square, which can also be proved. If you feel that something very different and very knowledgeable and very informative has been discussed today, please do not forget to give us a thumbs up for this video. Please do not forget to subscribe to our channel. If you have already done so, click on the bell icon and select all so that you can start receiving updates from us regularly. If you want us to do some specific videos and specific topics, please do not, please mention it in the comment section so that we can do it for you. Thank you so much. Until next we meet, goodbye.